Hello everyone, and welcome back to another video. And I have finally bought an oscilloscope, and I will be using it in content going forward. But I first want to explain really why I bought an oscilloscope, why they are so useful, and what you can tell or interpret from the data that it's going to be giving out. Because a lot of people seem to be confused about what an oscilloscope really does. That comes from people on Buildzoid's oscilloscope videos just not getting what the video is about, and also me witnessing people use oscilloscopes at university and not having any idea what they're doing. So I will give my best attempt at trying to convey why you want an oscilloscope and why it is so useful and how you can use it to tell how good the power delivery for a certain part is in this video. So yeah, we're doing some theory first, and then we're gonna have some fun with my Rigel DS1054Z. So first off, right here I have a nice neat graph. The y-axis is voltage and the x-axis is time. Specifically, the time axis is on the scale of a few nano to microseconds. So it is a very, very small time frame. And yeah, so let's just say we have a CPU and we want to run 5 gigahertz on that CPU. And let's say it needs 1.25 volts set in the BIOS to run 5 gigahertz, which is what we see right here. So we set 1.25 volts and our CPU runs 5 gigahertz and everything is fine. And just to make sure that we're actually running 1.25 volts, we take a multimeter, the line that's in green right here, and we check at a capacitor that's reasonably close to the CPU, or somehow we manage to. Sometimes you can probe the dye sense circuit, or let's just say we look at the dye sense voltage in hardware info, and we make sure that our dye sense is actually 1.25 volts. So yeah, and we're gonna see a nice static 1.25 volts. Everything is fine. Our CPU runs 5 gigahertz, and that is good and well. But now, for whatever reason, we swap out our motherboard. Specifically, our first motherboard that we did 5 gigahertz on was a pretty nice and expensive motherboard. But for some reason, we can't use it anymore. So now we're going to get a cheaper motherboard, a motherboard that's still can overclock but is rather cheap, an entry-level motherboard. And we again put our CPU in that motherboard, we set 1.25 volts in the BIOS and set 5 gigahertz, and now our CPU blue screens. It no longer runs 5 gigahertz. But we check hardware info, it says 1.25 volts. We take a multimeter and probe in the same spot again. It says 1.25 volts. So what just happened? It's the exact same clock, the exact same voltage as before, but our CPU no longer works correctly. Did we degrade the CPU? Is something wrong? Is there something broken? No, there isn't anything broken. The cheaper motherboard simply has a worse performing VRM. That is not as good at transient response, that's just generally worse at voltage regulation and has, worse voltage delivery. But our multimeter and hardware info, they can't tell us that. They will show us we have 1.25 volts and we know we need 1.25 volts, so why is it not working? Well, that's coming back at the time scale. So, the green line is what a multimeter and hardware info will tell you. The yellow line is what's actually happening. But because this is all happening in a few nano to microseconds, our multimeter and hardware info just can't tell. Those sensors are not nearly accurate enough to see those small fluctuations in our operating voltage. We need an oscilloscope for that. So we can't really tell what's actually going on with our voltage until we take an oscilloscope. And when we take our oscilloscope, we will see that, the yellow line is what we get on the first motherboard. But on the second motherboard, it's going to look kind of similar, except that at this point, we get this. We have a lower minimum voltage and also a higher maximum voltage. The average remains the same. That's the green line. The green line is exactly the same, it's 1.25 volts, but our cheaper motherboard has a minimum that's at around 1.175 volts, whereas our expensive motherboard has a minimum around 1.2 volts. Now there are many reasons for why that minimum is lower, but the important bit is, when our voltage drops down to that minimum level of voltage, which has many causes. Usually it's just because the CPU or GPU or whatever we're trying to power is experiencing different levels of load. Even if it's 100% utilized, different actions are different levels of load. Specific parts in a frame render cycle are harder and some are lighter. Sometimes you are just waiting for memory access and you pretty much do nothing even though you're technically doing something all the time. You just have to wait to actually start working on the data. You're just waiting for your memory or VRAM or whatever to send you some data. That is low load, and once the data arrives or some other task in the frame render cycle starts that's really heavy, you start doing a lot of work very suddenly. And given that CPUs, like our CPU right here running at 5 GHz, newer graphics cards are getting close to 3 GHz, that is very fast. Those are, you take 1 second, you divide it by 5 billion, that's how long a single clock cycle is at 5 GHz, and that is even shorter than a few nano or microseconds. So our voltage ripple is actually quite slow compared to the actual operating frequency of our part, which even most oscilloscopes can't see. Like the oscilloscope I have, for example, takes 1 gigasamples a second, so it can take 1 billion samples a second. Well, if your part runs at 5 billion cycles a second, then you only see every 5th cycle. And your resolution is kind of bad because you can't really tell what's happening in between the cycles, you just see a peak or a valley or something. So yeah, that's why the oscilloscope right here is set to a scale of nano or microseconds, because that's what a normal oscilloscope can actually see. But yeah, so because our worse VRM is, it's cheaper, it's worse, it has less capacitors, it doesn't have a high-end voltage controller, it doesn't have as many phases, it might be using lower quality components, all that lead to worse voltage regulation. And when that load hits, our voltage drops further. And that is what you will see in this lower minimum. And you can really only see that with an oscilloscope, because the oscilloscope can take so many samples per second. Like my oscilloscope takes 1 billion samples a second. So every 1 billion times a second, I can check what voltage goes into my CPU or graphics card or whatever. And every now and then, you will see these minimums, which happen. And yeah, depending on how good your VRM is, if it's better or worse, or if you have modded it versus stock, you will see different minimums for the same average voltage. That's why on a cheaper motherboard, you will need to set your average voltage higher to get the same clock as on a higher end motherboard, because the lower end motherboard has a sharper drop for its minimums. Or that's also why cap mods work, because cap mods do the opposite. They increase the minimum because your voltage drop is less, because you have some energy stored in your capacitors, so when the voltage drops, the capacitors release that energy and counteract the voltage drop so that it doesn't drop as low. And that's really what it's all about. That's what the oscilloscope can tell us. We can take two VRMs, put the same load, the same average voltage on them, and then observe what happens. And the VRM that will drop lower is the worst performing ones, and it's going to need mods, or you're just going to need to run a higher average voltage to get the same overclocking capability out of it, because again, these spikes happen on a few nano to microsecond basis, but your part operates way faster than that. Again, 3 to 5 billion cycles a second. That's like, I don't even know what the unit is, but way smaller than a nanosecond. So while your minimum is down there at 1.175 volts, your CPU or GPU is going to do hundreds, if not thousands of clock cycles at that lower voltage. And if that voltage is too low, like we know that with an average of 1.25, we can run 5 GHz with minimums of 1.2. But if our minimums go lower to 1.175, we can no longer run that. The CPU is going to crash. And that's exactly what happens. We haven't changed the average. In hardware info and to our multimeter, it looks like we are running the exact same voltage into the CPU, but it no longer works at 5 GHz because of those minimums. And that is basically what it's about. Because the oscilloscope will show you a graph like this, it will give you measurements like your average, your minimums, it will even give you your maximums, those are way less important. And that's the important bit. That's what I want to show, that's what I will be measuring with the oscilloscope, and I hope I can get a few good examples and just be able to show you what's happening, because really an oscilloscope is the only piece of equipment that can actually visually show you how your VRM is performing or how mods you're doing to the VRM are affecting it, outside of just, oh, my thing runs a higher clock now after I did those mods. And yeah, that's what it's about. That's the theory part done. This is, yeah, like the only thing you need to remember is that your multimeter and hardware info, those sensors are fine. They show you an average, but they cannot show you those very small deviations which happen. Transients do happen all the time. That's just how physics works. You cannot get rid of them, you can counteract them with higher end VRM design. And our oscilloscope will show us which VRM design is the best. And yeah, with that, I think it's time to actually go give you an overview of my oscilloscope, how I currently have it hooked up. It's not a great hookup method right now, I need to invest into a better one, but it's gonna be fine for demonstration for now. And then I'm going to demonstrate some of these graphs on a GTX 480, because as we all know, the GTX 480 has an awful stock VRM, so it should be perfect for showing those voltage deviations. So be right back. So here it is. This is a Rigol DS1054Z. If you've watched Buildzoid's oscilloscope videos, you should be probably familiar with what this thing is, because as far as I know, he was using the exact same one until he recently replaced it with a much more expensive oscilloscope that I would never be able to afford. But yeah, so this is a fairly nice oscilloscope. It's kind of known as a value option. I got this one fairly cheap as technically used, but apparently the seller never really used it because it is basically new. And this even came pre-unlocked to 100 MHz bandwidth by having a nice firmware flash on it, because now it self-identifies as a DS1104Z now instead of a DS1054Z, which as far as I know is just the 100 MHz version of this oscilloscope right here. So yeah, right now you can't really see much on screen. You can just see, you know, an empty graph, nothing's really happening. And you can also see, yeah, just kind of empty measurements, but these are the measurements that we can see. Here's the minimum voltage that I talked about. RMS is the average, and our maximums are, you know, our maximums. And then VPP, you can probably kind of guess from the image. VPP is the difference in voltage between the maximum and the minimum, which is a general voltage, a general measurement of how good your VRM regulation is, but it's not an absolute one, because you can get better VPP by reducing your maximums, which does nothing for your overclocking, but it does reduce VPP. So don't take it for an absolute value, but it is a pretty good general indicator of how much your voltage swings around. But really the important bit is the difference between the minimums and the RMS, or average, as I've called it before in the theory section. Now, as to what we're going to do, here is a reference GTX 480, and I have hooked up the probe to the back of it. Now, this way of attaching it is not good. I will try to get a better thing done. Many people have been suggesting to buy a BNC cable, cut it, and then have a proper hookup soldered to a multilayer ceramic behind the card right here, because using, you know, a regular probe, especially using this ground alligator clip right here, can really screw with your results. But for now, this is all I got, and the results already look pretty good. It's just what you're seeing right here is not gonna be the most precise reading ever. It should get better once I can find a way to like get a proper BNC cable that I can turn into, you know, a way more accurate measurement probe, and little adapters that I can, you know, put on the card instead of... Right now I'm just soldering some capacitor legs to the back of a multilayer ceramic, which is also structurally kind of a disaster. So yeah, this is why I'm doing it on a 480 and not a 1080 Ti. But yeah, so probe is hooked up to the V-core VRM of the 480 directly behind the core, which is basically the, well, reasonably the closest we can get to the GPU core to measure voltage, because due to power plane resistance and inductance and all the other physics things that are happening, our voltage does drop from the output of the VRM to the part we're actually trying to power, so we want to be as close to our power consuming part as possible. And on graphics cards, the backside of the core is usually the spot to go. So yeah, I'm going to start this thing up, and immediately, we just missed it because that board is turning off. There we go, and immediately we can see something happening on screen. So this is the core voltage of the 480 right now, and right now it's just kind of a bit of a fuzzy mess, probably because, because the bandwidth limit wasn't turned on. And yeah, we can already see some readings that are going to be very helpful. So we can see we have an average of just below a volt, and our minimums are at around 0.95 volts, so a little bit less than 50 millivolts of drop. Right now our core voltage changed because the card is starting up. We have a VPP of around 80 millivolts and a maximum of about 1.12 volts. Now this is just the card idling on the desktop. Once I start actually running something like GPU-Z render test, this will change. And you will now see these little spikes, and I can, you know, normally it looks like this. I can set a trigger, which will then sort of keep those spikes on screen if they are periodic enough, and now I can zoom in. And this is sort of what I just showed you in my example. You can see how the voltage is swinging up and down. And right now our trigger, you know, as you can see, is like triggered by a minimum. Every time our voltage drops to that minimum level, like you can see the trigger level is about 1.01 volts. Every single time our voltage drops there, we put an image on screen. And this is, this is basically the exact thing that I was trying to show to you on the screen. And you know, we can see our measurements. Our VPP is a lot higher now, and we are going from just under 1.1 volts down to below a volt. So we're dropping more than 100 millivolts, about 120 millivolts, from our average to the minimums. So our card is consuming as much power as it would be if it was running at only 1.1 volts. It's generating about the same heat it would be if it's only running at 1.1 volts, but it's overclocking like a card that's running at 0.97 volts, because the minimums matter. This is not that much. You can see this is only 20 microseconds per division, so every square is 20 microseconds, but that's long enough. Even this old GTX 480 is running at 750 megahertz. That is 756 million cycles a second. So that's quite quick. That is a lot quicker than those couple microseconds. And many clock cycles happen while the voltage is that low. So our overclocking is represented by this number, whereas our power draw and heat output is represented by this number. Now, I'm going to run something more intense. I'm going to run Unigine Tropics just because it's a nice periodic load on it. And now we can see an even more interesting waveform. It's actually not too much different, since GPZ render test on a card as old as this is actually quite intense already. But this load is now drawing a bit more power. And I mean, you can see a bit more distinct spikes, because now the card is really heavily under load. It's 100% utilized, and you can see a very sharp drop off. Like we about our average is about here, and it goes up a little, jumps around, and then we have this big drop down before it goes back up slowly. That's another voltage drop. And I can make this even worse if I stop the test real quick and go open MSI Afterburner and set our voltage to 1.213. The card will now be drawing even more power because it's running at a higher voltage, and our spikes will be even worse. Now I have to actually put the trigger back up because our voltage has changed. But yeah, now our spikes are even worse, because the more power you draw, the more significant those spikes are going to become. And yeah, like this is what the card looks like running Tropics. And an interesting tidbit is, you can see we're running at about, the FPS do change from a scene, but we're running at fairly okay FPS here. And if I zoom all the way back out, you can see that the signal becomes very periodic. And every single one of those periodic just places in the signal, that is one frame render cycle. That is one frame being rendered by the graphics card. So every single time something repeats, that's another frame render cycle starting or ending or doing a specific thing. And by calculating the difference between those periodic parts and then taking into account your per division time, so right now we're on a scale of 10 milliseconds per division, you can actually calculate your FPS that you're running at by looking at this, because that's just actually what we're running. Sorry, can't talk. That's actually just what we're looking at. This is the card doing its thing. This is the card rendering right now about 97, 98 frames per second. And if we zoom back in, you can of course see our worst case minimums where the voltage goes really steeply down. Actually, if we zoom back out, get a few more measurements for us, we can now also see, let me clear the statistics for a bit from when we had a lower voltage earlier. And now you can see, oh, VPP is really bad. Like that is really bad. So our average is 1.24 volts, actually slightly above what we set, but that's probably just because my measurement hookup is not the best. It should be actually slightly below 1.213 volts. But you can see we are losing quite a lot of voltage. That's about 120 millivolts that are just gone from my average. So yeah, the card's using as much power as a 480 at 1.24 volts. But assuming perfect VRM voltage regulation, your card would be overclocking a lot better than it is right now, because it's overclocking like you're running at a 1.1 volts or slightly above that, because that's just how transients work. Voltage goes up and down. And yeah, our maximum is actually going quite high. They don't really do anything. Like, your maximums can go way higher than this and they won't really do any damage. A lot of people get very freaked out when they see voltages in excess of 1.3 volts. This is not a problem, because again, we're on a scale of, well, right now actually microseconds, but if I zoom back in to show one single transient happening, that's 50 microseconds, or 20, or 10 microseconds per division. Like, the actual transient event itself is very short. Actually, if I just press single, it will capture a single transient for us to look at. and if we now zoom in, the actual transient event is, you know, it's, yeah, about 10 microseconds. So, yeah, pretty long in terms of the GPU, but pretty short in terms of real time. So let me unpause it. And yeah, so that's what you can do with an oscilloscope. That's the nice thing you can do with one of these things. And yeah, primarily I'm going to use it for just showing what certain mods do to cards, how good cards are compared to another. Like cheap-ass chips is going to start soon with the HD 58, was it? No, 6850. I will compete in that. These cards seem fairly cheap. I'm probably gonna get one or two, and I do plan to e-power one of them. And having this oscilloscope now is a perfect opportunity for that, because I can test the quality of voltage regulation before I e-power it, because those cards have fairly pathetic 3 or 4 phase VRMs. Now I'm going to probably put a GTX 480 power board on it, which has 6 phases. So that could potentially drastically upgrade the voltage regulation quality. That plus me putting a lot of capacitors on the card and doing whatnot I can do to improve the card's, you know, overclocking capability. And using this oscilloscope, I can now actually visually represent, visually represent with this and represent with very precise number measurements once I actually figure out how to hook up my probes with this, how good that VRM is and how much better a e-power can actually be. I've actually already done some scope shots of 2 cards I e-powered, and actually I'm surprised that they are not that much better. In some ways they are actually worse than a stock VRM. Not in ways that really matter, it's mostly just your maximums goes up because of how e-powers are usually implemented without forward voltage sense. But it's interesting to see that just putting an e-power on is not really everything that you need to do. You need to do a lot more things than just slapping an e-power onto a card to make it really, really clock well. And yeah, at least that is gonna be a thing. I'm basically just gonna hook a bunch of things up to this oscilloscope, and whenever I see something interesting happening, I will make a video about it. And of course in the future this will be very, very useful for me knowing what are my mods actually doing. Are they actually helping the card? Should I continue putting capacitors on this, or is the voltage regulation already good enough that I don't need to bother? And yeah, it's just a really, really, really useful tool. I've been told by several people that once you have an oscilloscope, you really question how you could live all those years without one. And I'm beginning to feel that. But yeah, I think the video is long enough now. You can expect a lot of content from this thing in the future. And yeah, if you're still here, thank you for watching, and until next time, goodbye.